Hi friends, in this video we are going to solve this problem. So this is here one optimization problem with constraints. So in this problem we are going to use Lagrange multiplier method. Why means because my constraint is equality constraint. So Lagrange multiplier we can apply only whenever the constraints are equal. So what is the problem? It says we want to find the point x1 comma x2 on the line x1 plus 4x2 minus 16 equal to 0 that gives the highest possible values for the surface x1 times x2. So first step, I want to write the Lagrangian. Lagrangian we usually denoted as a L of x1 comma x2 comma lambda 1 lambda 2. The lambda 1 lambda 2 is how many constraint will be there. So here only exactly one constraint only there. So we want to write lambda 1. So lambda only there. So I can, for the notation content, I simply stick with lambda. If the two constraint means lambda 1 lambda 2, I have to introduce. Now first of all I want to write this here constraint f of x1 comma x2 minus or plus, because lambda has here either positive or negative. So I can choose minus lambda. Some people they prefer plus lambda. For this example I use the minus sign only, times g of x1 comma x2. So what is f of x1 comma x2? x1 times x2 minus lambda times x1 plus 4x2 minus 16. So this is, so first step I want to use the necessary condition. What is the necessary condition? Necessary condition is dou L by dou x1 equal to 0, dou L by dou x2 equal to 0 and dou L by dou lambda equal to 0. So how many decision variable? Those derivative I want to take partially with respect to decision variables, our Lagrangian. Similarly, how many Lagrange multiplier will be there? We want to take partially, then equal to 0. The first step I want to calculate what is dl by dx1. If you take partially with respect to x1, here only x2 only will be there, x2. So if you are take derivative with respect to this one, you will get it as minus lambda equal to 0. This implies x2 equal to lambda. Second, dou L by dou x2 equal to 0. So first write x1 minus 4 times lambda equal to 0. This implies x1 equal to 4 times lambda. Next third one is dou L by dou lambda. So whenever you take that, the corresponding constraint only will come. So constraints are x1 plus 4x2 minus 16 equal to 0. So x2 is lambda, x1 is 4 lambda. So we will get it as 4 lambda plus 4 lambda minus 16 equal to 0. This implies lambda equal to 2. So this is the lambda equal to 2, we will get it. Second thing, so lambda equal to 2 means x2 equal to lambda. So x2 value also 2. So x1 is 4 times lambda. So x1 equal to 8. These are the stationary points. So that is why these are the stationary points. So that is why few people they called us this one as these three equations together. We called as the stationary equations. Now, so this is for the, now I go for the sufficient condition. I know that this point, it may appear for the relative maximum or relative minimum, sometimes saddle point, those things is possible. So second condition is, we are going to use, whenever unconstrained problem, we are going to use the Hessian matrix. So in this case, whenever constrained, we call it as a Bordered Hessian. Those things we are using, that is given, some people they called as a Hancock equation also. So this is called as a Hancock condition or Bordered Hessian. So some people they call it as a Hancock equations, or this one is L11 means you want to take the Lagrangian with respect to their distant variables. G1 means first constraint you want to take derivative with respect to the first distant variable. G1221 means second constraint with first variable. So using that, we have only two distant variables. So our Bordered Hessian is our Bordered Hessian is, you want to take the determinant dou square L by dou x1 square dou square L by dou x1 dou x2. Then first constraint, so we have only one constraint dg by dx1. Second is dou square L by dou x2 dou x1 dou square L by dou x2 square g by dou x2. Here is dou g by dou x1 dou g by dou x. So here minus times z will come, that's safer. Z2, here you will get it as 0. This is equal to 0. If the two constraint will be there, means g1 dou x1 dou g2 divided by dou x1 only will come. So this is the Hancock condition. So first of all, I want to take the twice derivative. So what is the dou L by dou square L by dou x1 square. So dou L by dou x1 we already calculate, that is x2 minus lambda. So x1 is independent, this function. So it is become 0. Dou square L by dou x1 dou x2. So you want to take first derivative with respect to x2, then you take derivative x1. So we will get it as 1. So the same value only we will get it for dou square L by dou x2 x1 also. Dou square L by dou x2 square equal to, so x2 is already x1 only, so it's independent of x2, so we'll get it as 0. Dou g by dou x1, dou g by dou x1 is, g is x1 plus 4x2, so x1 means we will get it as 1, dou g by dou x2 means we will get it as 4. So now I will find the bordered Hessian. So 0 minus z is minus z. So we will get it as, this one is 1, this one is 1, second row is 1 minus z, here you will get it as 4, 1, 4 and 0. Equal to 0. Now I want to find the, so clearly the Hessian, border Hessian is a, here z minus z. Here minus z power number of descent variable minus number of constraints. This order only will come. So that meaning is we will get it as this equal to minus ez, we want to determine value only. So minus ez 4, 4, 0 minus 1 times 1 g 1 4 1 0 plus 1, so 1 minus z 1 4 equal to 0. So this guys become 16 ez minus plus 4 minus plus z, correct, plus 4 plus ez equal to 0. We will get 17 ez equal to minus 8. Ez is equal to minus 8 divided by 17. This is less than 0. So whenever the Hancock condition, what it says, whenever ez is negative, the correspondingly stationary points are relative maximum, ez is greater than 0 means relative minimum. Third condition is, suppose z is either positive or means we call it as a, so z is equal to 0 means it's a test fails. Z is sum of the, because it's sometimes degree 2 also possible. Some z is negative, z1 is negative, z2 is positive means we call it as a saddle point. So here it's negative, so this implies the given function is at stationary points, the function is maximum only occur. So now you want to find the f of x1 comma f of x2. F of x1 is 8, x2 is 2. So this implies value is x1 times x2, we will get the 16. This is the maximum value. I hope in this video how to find the equality constraint problem using the Lagrange multiplier method. Then we are conditioned the necessary condition how to find the stationary point. Second, using the Hancock condition, find the sufficient condition also. Thank you for watching this video.